saying a little bit ago, we're going to spend the first part of class finishing up the PowerPoint. We've got servo motors and I believe maybe permanent magnet motors left. Nope, servo motors is the last thing we have to talk about. 8 slides left of that, and then we are going to go. These I have right here in my possession. 81 of the 95 questions of this test. I plan on reading through each one of these. The actual question. We will discuss the answer and move on. So those of you who hear something that you don't remember reading about in your book, now these are questions directly from the book. Okay? There's a few of them that I'm going to add that are questions from the lecture, but these are directly from your book. So if you hear something that you don't remember, it may be in your interest to write it down and review it. Okay? All right. I'm not too concerned about Phil anymore. I feel like he's kind of made it apparent what his decision on regarding our class is. Okay. Servo motors. These are really neat. Servo motors are really neat little deals. I'm actually going to get this real quick because I got a little bit of video of this. So I don't know if you guys remember my first little days activities where I would explain to you guys a little bit about me. But these right here, remember what those are? Those things are right there called bottle wing outs out of the core plant. We move the bottles out after they get formed. Each one of these, on this particular machine, I think there was 12 or maybe 14 of these. These are servo motors. There's a plug over in that place. You see servo motors that this part right here is an air actuated roll. Cylinder that shoots out, gets a hold of the bottle, and then at that point, it swings them out here and goes along the conveyor belt right into the rest of the process. So that's a servo motor right there. Here's some of the parts. I'm not going to require you guys to know the parts because if the servo motor goes down, you just throw it right into it. Okay? So we're just gonna. I just wanted you guys to see actually what's going on inside here. So I wanted to just review this with you and just show you. The actual amount of servo motors that are around in industry. So the volume, oh, you butthole. Hold on. Wowzers. That is moving that thing huge. What is happening here? I don't know what's happening. Yeah, it is, but I'm trying to get it to slide over. That's what I want. That's what Brian wants. Okay, now we're where I want to be. All right, thankfully we haven't really seen any, but bam. Okay, so I'm going to run through this again, and I'm just going to point out to you guys all of the actual servo motors that are happening on this particular piece of equipment, because each rotation, each movement on this thing is a servo motor. Once I get up here to where I can see these. The conveyor belt motors aren't, those are just regular old 3-phase AC induction motors that are pulling the bottles in there. But, okay, I'm going to maybe go a little, no. All right, so right here. So this device right here, this is called a stacker. As you can see on this, what this is doing is it's going this way with this bullet bottles, lifting up these are air seal lines inside of here, they're lifting up over top of the thing, all your bottles, and then As it comes over, it's shooting over, lifts up, and comes back. So we have a very simple forward and back motion. So this is the perfect application for a servo motor, and especially a DC servo motor, because they're so easily changeable just by changing the direction of voltage, like we did with my Friday lab out in the lab. We changed the direction just simply by changing low voltage. Yeah, that's why these things are so neat. So that's a servo motor that's running that guy right there. It's just simple repetitive motions where these things go and do their real work. So that simple motion right there, go forward and back, forward and back, forward and back. That's an air solenoid right there that's going to do that, but you could probably get away doing a servo motor there too, but air solenoid is more practical. Okay, come on now. So there's several here that I wanted to illustrate to you guys. We're going to see the next one right here. Okay. Now this right here, this part is called the pallet, right? And what we have in here is these air solenoids are going to come down to these pallets, and then as this thing rotates out, or comes out toward the rest of the pallet, you're actually going to see the walls rotate. There's also a servo motor that's rotating above, okay? And there's also one that's moving the table that they're sitting on, and there's also one moving this whole little plant. So watch that motion happen. And this thing, so this is one of 5 of them. At least there's $3.4 million a day that get processed through these 5 conveyors. These are pallet. So see that motion of how we're spinning one way, stopping, spinning back the other way, stopping, spinning one way. So that constant change in motion is the perfect spot for a DC servo motor. In this particular part right here, the up and down motion and the side to side are also both servo motors. They are similar, but since it's DC, we don't change the frequency, we change the voltage. They're DC digital drives, so the variable frequency drive is meant to be on an AC system, because that's how we control the speed of an AC motor, is we increase or decrease the amount of pumps going to the actual windings. And here all we have to do is change the voltage to the speed of the voltage, lower or higher. Okay, that's pretty much all I wanted you to see on that, was that these things, you know, to me, when I see them in the book, when I see a servo motor, look, it doesn't really hold any value to me. Okay, great, it's servo motor, what is that? Am able to see that? But that's more or less the same thing as DC motors in general. For those motors that we have out there on the bench, you guys are very probably see it. It does matter if you go online. Okay, you'll see it every day. They're all over the place because of the simplicity and easiness to increase or decrease the speed. So servo motors, here's where we actually have something that if you guys find yourself in the manufacturing facility, that we even have here in Rapid, there's a place called the Core Panel makes cabinets. There will be most likely servo motors on their process line. Okay, this is something that you can actually see, and that's why I put that in there, just so you guys got an actual visual representation of, okay, yeah, I am going to actually have to deal with these. So, okay. So characteristics of servo disc motor. Now, a servo motor and a servo disc motor are 2 separate things. I'm going to read through this with you real quick, and then I have actually a couple examples down here a little deeper that I'm going to explain a little bit a lot more. So servo disc motor act differently than permanent magnet motors. PM motors, permanent magnet motors with iron armatures, have clogging problems at low speed, and disc motors run smoother. So when we're talking servo disc, keep in mind that we've changed from having the iron core armature that's running the length of the machine. Now we have a little disc, and I'll show you pictures of it in just a second. So low inertia disc motors accelerate extremely fast. So low inertia, who knows what inertia means? Mike? You know what inertia means? One of Newton's laws. So we just draw this real quick so we have an idea. Inertia. An object going in motion tends to want to stay in motion unless acted on by equal or greater force. So when we're talking low inertia, we're talking about something that doesn't take a lot of force to get it moving. That's what we're talking about here. So as this car is coming around here, inertia is telling it that, hey, you don't want to turn, you want to keep going straight. Okay? Well, making the car turn is the friction to the road, and returning the steering wheel, the friction of the tires plus gravity. Big on physical form of the that's what it's low inertia means. Not doesn't take a lot. Like you put a DC motor on there, you feel the spin on it. You can actually feel you're having to put muscle on it. You already know about here, but now you can spin on this.
Okay. And speed varies with voltage, obviously, which varies with pulse width modulation. I think, did it save? Nope, didn't save on this part, but we're going to talk about pulse width modulation too, because I want to make sure you guys knew that, because I heard about it when I was in school. It didn't really matter to me because of the DC motor technology. It is something that we should probably at least touch on. Pulse width modulation, and I think I have some explanation in here a little deeper. So moving forward, DC servo disc and servo disc motors. DC servo motors are small permanent magnet motors with lightweight armatures that have very little inertia, so they operate at high speed and stop and reverse quickly. So these little guys are perfect in robotics, right, Dave?
Yeah.
Yep, perfect in robotics. Like when, say, you're trying to engineer a hand.
You got really tiny disc motors that you're controlling all three controls in one hand. They're startable, and they start so fast and they move so fast that you can almost have
The same motion as a finger. Okay. Servo disc motors and servo motors with very different armature design. So armatures contain copper conductors on thin disc printed on fiberglass with no iron armature. So these are kind of throwing our old DC motor anatomy out the window. These are quite a bit different, but they operate on the same principle. So current in the conductors produces a magnetic field, torque, form commutator on one side of the armature. So, all right, that's what the book has to say, and now we're going to talk about the stuff that I added. So a servo motor is basically a DC motor along with other special purpose components that make it a DC motor servo. In a servo, where's my mouse? In a servo unit, you will find a small DC motor, a potentiometer, a gear arrangement, and an intelligent circuitry. The intelligent circuitry, along with the potentiometer, makes so the servo can rotate according to our wishes. As we know, a small DC motor will rotate with a high speed, but the torque will generally be generated by rotation will not be enough to move a light load. This is where the gear system inside, I don't know if you guys, my lab the other day was paying attention, but when we were running our motors, a couple of you guys, I reached out and just stopped. Because the magnetic field is not powerful enough to actually keep it once you plug it up. So some of you guys maybe saw me reach out and stop. It's because although it seems like those are going pretty fast, the torque is very low because we have a very small magnet. This DC servo motors have a little bit of a different capability than that, just because of how they're designed in that circuitry. And plus also the gear mechanism, because we're going to increase or decrease our speed or our power just by adding some gearing, kind of like the transmission in your car. The engine RPMs can only go to 8,000, but it's the transmission that makes the car go fast and slow. So that's essentially what we're saying. Okay, so the gearing mechanism will take a high speed input of the motor, which is going to be the fast part, and the output will be generally lower. The output speed will be lower, and you'll have more torque just from the gear ratio inside of there. So that's the combination of all three of those. Yeah. All right. So here's what we're actually talking about. The inside, when the pictures that I looked at the book are all, they're not in color and they're kind of difficult to see. This is actually a full color picture of what that armature looks like.
So what's going to happen here, and here's a kind of a little bit of a diagram here, is with the circuitry that's happening with this, we're actually going to be able to put voltage on each one of these little bitty pieces of conductors here, and that is what's going to create the magnetic field inside of here, and it's going to oppose the permanent magnets here. So the housing, obviously basically the same thing as the frame, but we have the bearings, and then we have here, right here, the stator, which is the non-movable side, is basically just going to have permanent magnets in it. And what's going to create that magnetic field is obviously what we pass the current across, and then of course through these, I believe it's Fleming's left-hand rule law or something like that. One of those laws that we'll talk about. That opposition to that magnetic field from the current flowing through there is what causes the motor to rotate. So the armature windings of a pancake motor are printed on a disc, hence the term printed armature. The disc typically is made from non-magnetic insulating material such as fiberglass with copper conductors. The armature disc or rotor is located between two thin stator discs containing permanent magnets. The magnets are arranged with alternating north and south poles so that the magnetic fields between the adjacent pairs oppose each other. All right, so when a conductor with current is placed in the magnetic field that is perpendicular to the current, which is what we have on with the green picture there, the direction of force is perpendicular to both the magnetic field and the current. This force is known as the Lorentz force. Lorentz force. Was there anything in the book about Lorentz force? Yeah, should have been, I hope. I didn't read the chapter. This force known as the Lorentz force produces a torque that causes the motor to rotate according to the right-hand rule, or more appropriately for electric motors, the left-hand rule. Okay, because their operation is based on the Lorentz force rather than Faraday's law, as in conventional motors, pancake motors are sometimes referred to as Lorentz force motors. A unique feature of pancake motors is that in addition to the copper conductors, the commutator is also printed on the armature. This design allows the brushes to run directly on the armature surface. The lack of a separate commutator ring in conjunction with the flat overall design make pancake motors very compact, especially when compared to conventional cylindrical motors. Their thin design, along with low inertia due to the absence of iron, allows pancake motors to achieve extremely fast acceleration and deceleration. Okay, now my next little spot here, pulse width modulation. Who knows what it is? It's definitely one of the bold words in the book, something that you may want to make sure you know. Okay. Pulse width modulation is a modulation technique used to encode a message into a pulsing signal. Now, I don't know if that's exactly what your book says. That's what it means. Basically, what we're saying when we're talking pulse width modulation is we're talking about changing what the on and off. So here's our sine wave. Now we're going to have, so we're talking DC voltage. DC voltage is going to be a positive DC voltage. So when we're talking pulse width modulation, we're talking about the on, turning this signal motor on, and turning it off to maintain a certain speed. So when we're talking pulse width modulation, we're not talking about turning it on in certain intervals to maintain speed. It's kind of like pumping your foot on the gas whenever you're trying to maintain speed with your cruise control. Turning it on, letting it go full speed for a second, turning it off. Through that process of modulating the pulse width, so what this is actually going to look like. And then, so if we wanted to go slower, we put more space in between you wanted to go faster, we decrease the space. So, see what I'm saying? Pulse width modulation. So we're talking DC, so it's already going to be rectified from AC to DC, and now when we're talking pulse width, it's going to be how long we're going to allow that to be on. It's probably some high-speed switching. I haven't read the paper, I want to show them. It's usually going to be turned on or off by some sort of high-speed switching, like an SDR, or a triac, or a whatever it was.
So, looking at the times for the server motor, produce the pulse and is equal to the frequency of about 1 kHz. So, it's to take that point in kHz, AC signal and modulate DC through. So, probably not necessarily one of those.
Yeah, well, and the whole purpose of this is for speed control, right?
Part of the model is
Okay.
All right. So my following notes on pulse width modulation. Although this modulation technique can be used to encode information for transmission, its main use is to allow for the control of the power supplied to electrical devices, especially inertial loads such as motors. Okay, this is where that ball game comes into. All right, right hand motor rule. Now I didn't spend a lot of time with these motor rules because in the real world, you really don't mess around. Okay, I've spent a lot of time with electric motors, and I've never, since I left school, had to remember the right hand, the left hand, any sort of motor rules. However, we do have to remember them because they're in the book, and the test is coming out of the book. So, right hand motor rule. The fingers of the right hand can be used to determine the direction of our armature rotation. The thumb indicates the direction of thrust, forefinger indicates the direction of flux, north to south, and the center finger indicates current flow. Okay? That is what it is. So, for this purpose, remember that. Okay, finally, we're to the end, to the summary, right, Corey? Right, Corey? Finally, we're to the end. How rude. How rude of me to throw a ball at you and wake you up. Motors convert electrical energy into mechanical energy and operate on the principle of magnetic attraction and repulsion. Torque produced by a motor depends on the strength of the magnetic fields of the pole pieces and the armature, and is proportional to the armature current if field excitation current is constant. Remember when we talked about drag-ons and shovels? Okay, that's where that is especially happening, is we leave one of them constant and we vary the other one. That's how we can achieve speed control in the mining industry. So current flow in armature is limited by counter EMF. What's EMF again? Electromotive force. Good job, pretty close. That's what I would have thought too, for the most part. And armature resistance. Thank you, sir. Thank you for giving me my toy back. Okay. 3 basic types of DC motors are series, shunt, and compound. And it would be in my interest to remember how to draw them. The motor will operate at a base speed when full voltage is applied to both armature and the shunt field. To reverse the direction of the rotation on a brushed DC motor, Joe, on a brushed DC motor, sorry I'm so boring, what do? Yeah, maybe that's all you needed. Right. Joe, go ahead, and then you'll answer my next question, right? Okay. To reverse the direction of a DC motor, all you have to do is change the polarity of either the armature or the field. Okay? Brushless DC motors do not contain a wound armature, commutator, or brushes. Everybody remember the brushless DC? I got to find that thing before the next class. I've been looking for it and it's vanished, which is a crying shame because we need to take that apart next hour. Permanent magnet motors are used to use permanent magnets as the pole pieces, so we're not using an electromagnet, we're using permanent magnets, and do not require series or shunt field windings and are more efficient than conventional DC motors. Why do you suppose that is? Why do you think they're more efficient? I don't know about no friction. What I would think of when I was thinking about exactly. We are only using electricity to power one item, not two. And that's the armature circuit. Servo motors have a lightweight armature with low inertia, and disc servo motors contain an armature made of several layers of copper conductors and fiberglass. That, friends, is the end of the show. Whew. This was a long one to get through. Hopefully we'll be able to get back on track when we're pumping through one a day. Mike, the next stuff we're going into is chapter 18. Mike, chapter 18. For those of you who would like to remember that I usually throw a quiz, a bonus question in there about the next chapter. Okay, that's where it's going to come from, chapter 18. So I'm going to let the recording run when we're going through these test questions. So if you guys feel like, hey, I forgot that test question that I might need to know, these are going to be available to you. I've got all three of the lectures for the DC motor recorded. I have one from DC generators recorded. If you want those, I'll give them to you. Your book's going to be the best place to get the answers, though. Okay. Who's ready for notes? Everybody ready? Okay, I wouldn't try to write each one of these down because you're going to get behind. I'm not going to spend a lot of time on them. We're already 30 minutes into the class, so we've got 20 left. So if you guys want to holler out the answers, I'm just going to read you the questions. If you holler out the answers, I'm not going to spend time to determine whether they're right or wrong. Okay, but that way you can research what the questions are. Okay, so let me see. This is the one I want to start with. Counter electromotive force and back EMFs, these are true or false. Counter electromotive force and back EMFs are names for voltage induced into the armature of a DC motor. It's true or false? That's true. It's all right to operate a series motor with no load connected. What do you guys think? False for sure, right? Because we'll roll that damn thing up. Okay. A device that converts mechanical input into DC electrical output is a not a motor. Generator. The rotating part of the generator is called the component of a DC generator that converts the armature AC to DC is the armatures are wound to provide high voltage, high current, or some specific combination of voltage and current. The wind that provides low voltage and high current is this is one of the three different kinds of windings that we're talking about in DC generator. So we got map, we got solid leg, and we have wave. Okay. Armatures are wound to provide high voltage, high current, or some specific combination of voltage and current. The wind that provides low voltage and high current is the wind wound. Okay, it may be, but I would be sure that I knew that. Okay, the same exact question, the winding that provides high voltage and low current is the wind. Armatures are wound to provide that same question. The wind that provides a moderate voltage and moderate current is the line. Okay. Items that ride against the commutator
to make electrical connection are the blank brushes. Magnetic field is sometimes provided by electromagnets.
This is done by windings that are wound around blank. I don't know.
The choices are brushes, pole pieces, the armature, and the case.
Series field windings are connected in series with the armature.
They are wound with blank turns to fairly blank wire. Shunt
Field windings are connected in parallel with the armature.
they are wound with blank turns
Of fairly blank wire. The output voltage
of a series generator set
with the load
is set with the load when the load is connected or disconnected. I'll read that one again because I'm falling through it. The output voltage of series generators is set when the load is either connected or disconnected. We talked about that. That's how we look.
it's a connected or disconnected. That's your choices there.
The output voltage of a shunt generator is usually controlled by the amount of
Field excitation current, input voltage, input torque, or armature excitation current.
okay. The reason why these are sounding maybe a little bit like I have talked about before is because I haven't.
So that's part of why I assigned the review questions to get you guys to go through the book, be familiar with the book.
Okay. A generator containing
Both series and shunt field windings is called a blank generator.
that should be an easy one. A compound generator, the setting of the amount of currents in the series and shunt field windings determines the complexing, compounding, exciting, or differential setting. In a generator, the series field diverter is also called the series field shunt rheostat, series
Rheostat,
series field exciter. Those are your choices.
a compound generator has both
Series and shunt field windings, when those windings are connected so that they aid each other in the produced magnetism, the connection is called blank compound, so either cumulative or differential. A compound generator that has both series and shunt windings, when those windings are connected so their magnetic field opposes, that connection is called blank compound.
cumulative or differential.
A device that converts electrical input into mechanical output is called motor. Electrical input to mechanical output. Motor. Okay.
When the field winding of a DC motor is connected in parallel with the armature, the motor is called
Parallel equals
shunt. The speed regulation of a DC motor
is proportional to the blank, which would be applied voltage,
load torque, armature.
or field resistance. Perhaps
A compound motor has blank field windings.
three.
Three of them. That's it. It only has three.
No, series and shunt are combined. The cumulative compound motor connection means the fields of the series and the shunt field windings add, subtract, multiply, or divide. A compound motor connection that is rarely used is the cumulative or differential. It has exactly that definition. Which one is rarely used? In a compound DC motor control circuit, the field loss regulator will disconnect the blank if power is lost to the blank. Rotor armature, shunt field armature motor are your choices. The motor that does not contain a wound armature, commutator, or brushes is the blank motor. Just read it. Yes, I just read it.
Permanent magnet motors have blank efficiency than wound field motors.
More, because I just read it, right?
We just talked about it 5 minutes ago. Small permanent magnet motors have lightweight rotors are often used as stepping motors, automobile starters, servo motors, or ceiling fans. The servo motor, which has a fiberglass and copper rotor, is the blank motor. Anybody want to venture a guess on that one? Your choices are copper, copper glass, non-ferrous, or servo disc.
Servo disc is minus. If I had to guess, because the rotor of a servo disc motor is made from copper laminated onto a fiberglass disc, the motor is also called a copper laminated printed circuit or non-ferrous motor. Or it would be the printed circuit. So let me confirm that. 32, because that's what I would guess. I believe I wrote that. 32. No.
Printed circuit. Okay. Some DC servo motors have square wave input voltage to vary the motor speed. The on and off time ratio of the square wave is varied.
This is called blank modulation. Pulse with modulation. Pulse with modulation. A square wave voltage varies between 0 and 12 volts.
The positive pulses are 50 microseconds wide, and there is a 50 microsecond gap between them.
What is the average DC waveform? I bet you that's in there. I was in the book. We talked about that. Okay? Pay attention to that. That's why I'm going over this with you right now, so you guys can see what we did talk about and what we didn't talk about and what you need to study.
Okay, here's another one of those same kind of questions. So 2 of them, 3 of them.
One after this one.
A square wave voltage varies between 0 and 12 volts.
The positive pulses are 25 microseconds wide, and there is a 75 microsecond gap between them. What is the DC average of the waveform? Okay, we got 3, 4, 6, and 9 per volt. Okay, so you guys, let's see. Wednesday I'm going to be gone. Thursday. So if you get these questions in your book and you're unfamiliar with them, we can meet up with meet up for the test and talk about it Friday morning. Does that sound good? Sound good? What time is Scott's class start Friday morning? 8 a.m. If you have trouble with these, come outside my room, or if you want to be down here, and we'll talk about these if you have trouble. There's 3 of these questions on here. And this is just the first part. So the square wave voltage varies between 0 and 12. The positive pulses are 75 microseconds wide.
There's a 25 microsecond gap between them. What is the DC average of the waveform? 3, 4, 6, and 9 are your answers there. So find the formula, plug it in, see if you can come up with those answers. Okay? Counter torque is caused by the magnetic field.
Counter torque is caused by the magnetic attraction between the field poles and the blank magnetic field. Okay. We'll do that together. Arms, same thing. Same thing, but
Not the same thing.
how about that wrong? So armature reaction is the bending of the stator magnetic field by the blank magnetic field, also armature. A force that tends to cause rotation is known as torque. A force that tends to cause rotation is known as torque. Torque is a force that tends to cause blank.
Okay, that's the first section. Now I'm kicking around the idea, and I'll listen to comment about it. But I'm kicking around the idea of cutting, to just leave that section in and cutting this section out.
If I do that, that's going to decrease the amount of points per question you get. So that means that if the more you get wrong, the higher the volume of points that you're going to be taking off from time. So right now we're sitting about 95. So if we have 95 questions on this test, question's gonna be worth about a point and some change.
So you can get
30 questions around surveys. Okay, that's what I'm thinking. You guys can hear this. This one seems like it's a little harder from what I've seen. In the right-hand motor rule, sum equals thrust or the
direction of magnetic field, direction of armature rotation, strength of armature current, direction of armature current. Okay? Wrong.
C, in that thrust. Direction of armature rotation.
When more than one loop is used,
The average output voltage is higher and there is less pulsation of the rectified voltage. This pulsation is called when more than one loop is used, the average output voltage is higher and there is less pulsation of the rectified voltage. This pulsation is called bubbling, wave, ripple, or curling. Ripple.
ripple, ripple, ripple.
Blank left-hand generator rule can be used to determine the relationship of the motion of the conductor and the magnetic field to the direction of the induced current. Fulton's, Phillips, Fleming's, or Fielding's. It's going to be probably Fleming's.
Blank is characterized by the fact that the output voltage at full load will be greater than the output voltage at no load.
Alternating compound, over compounding, under compounding, or flat compounding. Over compounding. A generator is a device that converts blank energy to electrical energy. Yes. A blank compound generator has its field connected in such a manner that they oppose each other in the production of magnetism. So they oppose each other. Differential. Right.
Two factors determine the amount of torque produced by a direct current motor are the strength of the magnetic field of the pole pieces and
Direction of the turning force, strength of the magnetic lines of flux, strength of the magnetic field of the armature, direction of the magnetic field.
most large compound direct current motors have a protected device connected in series with the shunt field called the blank relay.
Shunt, armature, field walls, and shunt. There are three basic types of DC generators: the series, the blank, and the compound.
Yep. All right, man, I'm getting tired of talking. How much horsepower is being produced by a motor turning a load of 300 pounds per inch at a speed of 1375 RPM? There's another one of your formulas that you might want to touch base on. Your choices are HP equals 0.65, 7.65, 76.52, 765.19. Once again, if you find these and you're struggling with these questions, these formulas, Friday morning, all right? Field blank current in the DC current that flows through the shunt field windings. Field blank current is the DC current that flows through the shunt field windings.
Your choices are
Hesitation, relaxation, excitation, or resistance.
excitation. Small permanent magnet motors are used as servo motors, rebel motors, armor motors, or pole motors. Servo motors. Once horsepower has been converted to a basic unit of power, it can be converted into other power units, such as the following. And we have several sections that can be 2.36 watts equals 1 foot-pound per second. 1 watt equals 3.42 BTUs per hour. 4.99 watts equals 1 calorie per second. 155 watts equals 1 BTU per second. The following formula can be used to determine the speed of a rotating magnetic field when the frequency
and the number of stator poles per phase are known. I think we did talk about that one. You might correct me on that. 120 minus F divided by P, 120 times F divided by P. So know that formula. The following formula can be used to determine the speed. Oop, just read that one. Wave wound armatures are used in machines designed for, remember that? We just talked about it on the other one. Low voltage, high current, low voltage, high voltage, high voltage, low current. Series motors have the ability to develop extremely high starting torques. The average output, an average of about blank percent of full torque is common. So how many times full torque is common for a series motor? 200, 450, 500, or 275. Some converters that supply power to brushless motors produce sine waves, but most produce a trapezoidal DC, trapezoidal AC, triangular DC, hexagonal AC. Armature reaction can be corrected by rotating the brushes around the blank to shift the neutral plane. Rotate around blank, just less than, double the amount of, slightly greater to, equal to. Let me read that one again. Armature reaction can be corrected by rotating the brushes and amount blank the shift of the neutral plane. That's a weird question. An armature reaction can be corrected by rotating the brushes and amount just less than, double the amount of, slightly greater than, or equal to, shift the neutral plane. I would definitely check that one out if you were confused there. I was. Blank motors are often referred to as constant speed motors. Shunt. In the left-hand rule, the center finger shows the direction of the field flux, thrust, current induced into the armature, or the movement of the conductor. Okay, these next ones are going to be all true-false until that might be it. We got 2 minutes left. So I'm just going to read these off quick, so we're almost out of time. You can hear them and decide what you want in your head. The amount of compounding in the DC machine is controlled by connecting a high value variable resistor in parallel with the series field. To increase the amount of output voltage, it is a common practice to increase the number of turns of wire for each loop. If a loop contains 20 turns of wire, the induced voltage will be 40 times greater than that for a single loop conductor. A motor is a device used to convert electrical energy to kinetic energy. The amount of output voltage produced by a generator is proportional to 3 factors, including the number of turns per wire in the armature, strength of the magnetic field and pole pieces, and the speed of the cutting action or the speed of rotation. A permanent magnet direct current motor with an iron armature have a problem with clogging at high speeds. There are several ways of controlling the speed of DC current or DC motors. The method employed is generally dictated by the requirements of the load. One advantage of interpoles is that they restore the field outside their immediate area and are able to overcome all the field distortion. The efficiency of a motor can be found using the following formula: power out divided by power in times 100. Lap wound armatures are generally constructed with large wire because of high current. Many DC compound motors intend to operate in an overspeed condition and will actually contain 3 separate shunt fields. 3 basic types of armature windings are lap, wibble, and dogleg. Brushless DC motors contain a wound armature and commutator but do not contain brushes. The speed regulation of DC motors is proportional to the resistance of the armature. Counter torque is a measure of the useful electrical energy produced by a generator. When a load is connected to the output of a compound generator, the initial voltage produced by the residual magnetism of the pole pieces produced a current flow through the load. The voltage produced in all rotating commutators is alternating voltage. The amount of counter EMF produced in the armature is proportional to 3 factors: the number of turns per turns in the wire, the strength of the magnetic field of the pole pieces, and the speed of the armature. Almost done. 3 left. Compound motors can be connected as short shunt or long shunt, just as compound generators can. They can also be cumulative compound motors or differential compound motors. The armature of a servo disc motor does not contain any copper. When one direct current generator cannot supply enough current to operate the connected load. In such case, another generator is connected in parallel with the first. Direct current generators should never be connected in parallel without an equalizer connection. Okay, 81 of your 90 questions right there. It's all recorded. I tried to stay around here so it should pick up my voice real well. All right, so I will get this available to you for the test. I'll try to get it done tonight, so if you need to rehear what was said, you can sure go back over the last part of today's lesson and hear it. Okay, so